Hello guys, section 5.5 today. This is a super meaty section that can take quite a bit of time to work through some of the problems as you'll see today. And so rather than having these due tomorrow, I think that's a little unfair because I know some of you guys have other things going on. I will simply make all of these, this section 5.5, due specifically on Tuesday, giving you a couple extra days to work on it, which hopefully will encourage you guys to give it some extra time. So let's go ahead and get started on section 5.5. Section 5.5 deals with polynomials, and specifically the zeros of a polynomial function. The idea is to use a couple of big theorems we're going to talk about today: the remainder theorem, the factor theorem, the rational zeros theorem, and the complex conjugate theorem, as well as Descartes' rule of signs, to determine how to find zeros of a function. Let's remind ourselves of some terminology. Zeros of a function. The zero of a function is defined in a couple different ways. These are your x-intercepts. That's the first big detail. One of the big definitions to talk about is that these are always your x-intercepts. Your second big detail, not only are these x-intercepts, but these are also, if I have a is a 0, then f of a equals 0. In other words, these are values where if I plug in a, I will get out a value of 0. So this is the other standard definition for what makes something a 0, is that it's a number that when I plug it in, I get out 0, which makes it the 0 of a function. And lastly, these are factors, which we've seen before in the last couple sections. Factors, remember, are things where if I split the function apart into multiple components, I could then take those factors and solve them. If I use the word 0, it means an x-intercept. If I use the word x-intercept, it means it's also a 0. If I say, hey, when I plug in an equals 0, that means it's an x-intercept, which means it's a 0. If I say it's a 0, that means it's a factor. If I say it's a factor, it means it's a 0. These all fit together in the same basic definition. All four of these pieces have the same properties. They may look a little different. Like, for example, if I say a 0 of a function, that's usually where I'll list a number, like x equals 3. But if I talk about the intercept, it would be the intercept is 3, 0. If I talk about the 0 value, that would mean f of 3. If I talk about the factor, that would be x minus 3. And so all three of these contain the same information. They're just different views on how they work together. And so it's important to note that all of these are the same basic result and will be treated the same in your homework assignment tonight. Okay, now let's talk about our first big theory, which is called the remainder theorem. Now, the remainder theorem states that if a polynomial call it f of x is divided by x minus k, then the remainder is equal to f of k. F of k. What does this actually mean? It means that I can treat this one of two ways. If I don't want to plug in a number, I can divide by it and get the same result, which is a little weird. Like, no other math can do this, but this is because we're dividing by the specific factor of k. And because of this, and what we talked about last time, there are shortcuts to doing this, which means that if the function is nasty or difficult to work with, sometimes the remainder theorem is simply just a better way to get the answer faster and easier. So let's take a look at an example. And this is the big one. If you haven't noticed in the text, there's these things called these how-tos. These are great to illustrate exactly the process we're going to go through when doing problems like these. And in your homework, these are problems like number 14 and 18. Or at least one's just like it. So we're going to do number 14 and number 18 to kind of showcase, sorry, not 14, 18, 6 and 10. We're going to do number 6, we're going to do number 10 to kind of illustrate exactly how this property works. And notice how we're going to do it. We're going to use synthetic division to divide the polynomial by x minus k. And then whatever value we get is going to be f of k. And that's typically what we're going to be asked to find. So let's go to number 6. So the first piece is actually a direct complication of last time's material, meaning we're going to be taking our function and using synthetic division. Let's look at number 6. We have, for number 6, I am going to write this on a separate page. I'm going to try to start keeping all my notes on one page and then having any work we show on a different page. So let's look at number 6. Okay, number 6 states we have the function x to the 4th minus 9x squared plus 14 divided by x minus 2. And it states in the problem to find the remainder. Well, let's do that. I'm going to find the remainder by doing two things. According to our notes, we're going to use synthetic division first, and then the result is our remainder. Well, let's set up synthetic division. Let's set up synthetic division. We make our little box. Remember, outside the box, we take this term and we set it equal to 0, which means I would do x minus 2 equals 0 and solve. Add 2 to both sides to get x equals 2, which means we put a 2 out front. Okay? Next, what goes inside? What goes inside are the coefficients. So how many x to the 4th do I have? 1 of them. How many x to the 3rds do I have? None of them. How many x squareds do I have? Negative 9 of them. How many x's do I have? 0 of them. How many constants do I have? 14. Notice it's a great way to phrase this so I don't miss any zeros. I just ask, how many of the next one do I have? I have x to the 4th first. How many? 1. How many x cubes? None of them. How many x squareds? Negative 9. How many x's? None. How many constants? 14. And now I'm going to do synthetic division with the result being my remainder. So remember, to do synthetic division, we drop the first number, getting a 1. We then multiply this by our number up front, so that would make this a 2, and add them together. 0 plus 2 is 2. We then multiply this by our constant, which is 4, and add them together, which is negative 5. Negative 5 times 2 is negative 10, which is negative 10. Negative 2 times negative 10 would be negative 20, which means we get a result of negative 6. And this is, in fact, our remainder. So the question asks, find the remainder. The remainder is negative 6. Now, to illustrate the remainder theorem, it states that this should be equivalent to f of k, which in this case, that means this should be equivalent to f of 2. Well, let's test that theory. We're going to do f of x is equal to x to the 4th minus 9x squared plus 14. And what we're going to do is we're going to plug in 2. 2 to the 4th minus 9 times 2 squared plus 14. And if this is right, we should get the exact same answer. So let's try it. 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 squared is 4, negative 9 times 4 is negative 36. And then 14 is 14. Let's see, negative 16 minus 36 would be negative 20 plus 14. Negative 20 plus 14 is negative 6. Look at that. That's pretty cool. And that's the idea of the remainder theorem, is that this is always going to be the case, which leads us into more advanced problems, because the nastier this equation is, the easier this process is. Because imagine this equation had like a 26th power to it. Like, what's 5 to the 26th power? Like, most calculators can't even do that. But they can do this step much faster and easier. And so it's just a way we can always find the solution by using just a different approach. And this was number 6 to illustrate that fact. Let's now look at number 10 with the same basic principle. So, number 10. Number 10 states, we're going to again use the remainder theorem to find the remainder. Let's see what we got. Number 10, we have 5x to the 5th minus 4x to the fourth, it sounds like a pattern here, plus 3x cubed minus 2x squared plus x minus 1 divided by x plus 6. Okay, we're going to use synthetic division, and then the result should be a remainder. Well, let's set up synthetic division. Okay, just like before, I take what I'm dividing by, which is x plus 6. I set it equal to 0, and then I solve. Subtract 6 from both sides to get x equals negative 6, which means my number out front should be negative 6. I then take the coefficients of this function. How many x to the fifths do I have? 5. How many x to the fourths? 4, but there's negative 4 of them. How many x to the thirds? 3 of them. How many x squareds? Negative 2 of them. How many x's? 1 of them. How many constants? Negative 1 of them. And then I go through this process. So, let's do it. 5 would drop. 5 times negative 6 would be negative 30, which becomes negative 34. This is going to get nasty real fast, I can already tell. Negative 6 times negative 34. Negative 6 times negative 34 would be positive 204. Add this together, you get 207. Ooh, let's get nasty. Negative 6 times 207 would be negative 1,242, which becomes negative 1,244. Like, this looks bad, but I promise you in a second when we actually try to plug this in, it's going to get a lot worse, because there's some things I just can't do without a calculator, even still. So, negative 6 times negative 1,244. Oh my gosh. Okay. Let's think of one down here, I guess. This is a 1 here. Negative 6 negative is going to make it positive. 6 times 1 is 6, so it'll be 7. 2. So 7, 4. 6, 4. Ooh, this is hard without a calculator. Okay, add this together, which becomes 7, 4, 6, 5. And then I take negative 7, 4, 6, 5 times negative 6. At this point, I am going to use a calculator. I can't do it any farther. It just, my brain can't handle. So I take negative 6 times 7, 4, 6, 5, which is negative 44,790, which means negative 44791 is our remainder. Negative 44791. However, what does this also mean? This means that we also would get this exact same answer if we just plugged in negative 6. And it turns out that's actually right. It takes a lot of work to do so. You'd have to take 5 times negative 6 to the 5th power minus 4 times negative 6 to the 4th power plus 3 times negative 6 to the 3rd power minus 2 times negative 6 squared plus negative 6 plus 1. Like, this is in many ways worse to do than this. Like, I could do this by hand if I was willing to write out my multiplication. It would just take time. I don't want to do negative 6 to the 5th power. Like, that is negative... no, I refuse. Like, negative 72,000 something? It's big. And then timesing that by 5, like, no. Just hard no. Not happening. I can't do it. And so, like, this is much easier to do by comparison. And that's what the first couple of problems ask you to do. Is they ask you to figure out, okay, what kind of function will actually let you get to that answer without having to actually plug it in. And that's called the remainder theorem. So, first part of our notes, done. Well, let's talk about the next piece, which is the factor theorem. Okay, let's go to it. The factor theorem is the big part of tonight's homework assignment, as you can see by the notes and by what's in the book. Factor theorem, factor theorem, there's the factor theorem. There it is. Okay, factor theorem. K is a zero of the function if and only if. So I'll abbreviate IFF. X minus K is a factor. I'll take one more detail here that's important that I skipped out on up above. This also indicates there would be a remainder of 0. Which, if you think about this middle one, is just the remainder theorem, right? Because the remainder theorem states that if it divides by this, the remainder will be 0. Well, if we plug in a and you get 0, then dividing by a means the remainder would be 0. So, like, you get the idea here. These all kind of fit together very neatly. So what this theorem states is, if it asks you to find the zeros, you can use the factor theorems like this one, using synthetic division. And so this is one of the primary ways you can do factors. So the big consequence here, okay, the big consequence is you can use synthetic division to find factors. How do we do this? Anything with a remainder of 0 is going to be that factor. So, note the how-to. This is a really important how-to. We're going to use synthetic division to divide by the polynomial, and then we're going to check to see if it has a remainder of 0. We're then going to write that polynomial using the product of the divisor we had and the quotient we ended up with. And then lastly, we're going to try to factor that remaining piece so we can actually write this polynomial as a factored form. There's a great example of this right here, but I'm actually going to go straight to the text and do number 14 and number 18. So these are ones like 14 and 18. So let's do this. Let's talk about 14. Again, if you want to see another example, we're going to do 2 together, but if you want to see a third example, the way the book does it, it's right here. Let's go to 14 and 18. 14. It says we have f of x is equal to 2x cubed minus 9x squared plus 13x minus 6, and the factor we're using is x minus 1. So we're going to take this one step at a time using those previous things as a guide. So step 1, we're going to do synthetic division. And step 2 is we're going to confirm that our result has a remainder equal to 0. So let's do synthetic division. Let's set it up. I'm going to shortcut some of this. If I have x minus 1, it of course will be 1 on the outside. And our numbers are 2, negative 9, 13, negative 6. I then follow through synthetic division. Drop the 2. 2 times 1 is 2. Negative 9 plus 2 is negative 7. Negative 7 times 1 is negative 7. This gets me positive 6. Positive 6 times 1 is 6. Gives me a 0. So we know from our previous theorem that this means that x minus 1 is a factor. But now we have to do step 3. Once we've done that, we need to rewrite. How do we rewrite? We take x minus 1 times this quotient that's remainder, which is 2x squared minus 7x plus 6. All right. Step 4. We need to, after we've rewritten, see if it'll factor again. Because all this should end up as 3 different pieces, 3 different terms, which is what happens. I'm going to now use, on this piece, the AC method, which we talked about 2 chapters ago. The AC method means I take the first and last term, multiply them to get 12, Add them together, I should get negative 7. And the results here are negative 3 and negative 4. And now I'm going to use the AC method to get to my solution. So we do x minus 1 times this by 2x squared minus 3x minus 4x plus 6. Do my factor by grouping. Again, this is just AC method. If you need a reminder about how to do the AC method, you can look up the AC method. Factor by group, which this becomes, I take an x out. This becomes 2x minus 3. Take a negative 2 out. This becomes 2x minus 3. Which means I finally end up with x minus 1, which was our original term, times 2x minus 3. That's what was inside. And x minus 2, which is what's on outside. And this is the solution. Again, one more time, showcasing our steps here. And those steps are listed out in the text under the how-to, under this section. Nose the G. Right here. Use synthetic division first. That's what we did, synthetic division. Confirm that we get the remainder of 0. We did. That tells me that this is a factor. Then write the polynomial as the product of this times the quotient. Remember, the quotient is the leftovers, the 2x squared, the negative 7x, and the 6. And then finally, factor the remaining pieces and write the product as a polynomial. This is our solution for number 14. And this is how you do all the ones in this same section, where it asks you to find these pieces. So in our homework, that's all these. All these in the same basic way. Okay? So to re-illustrate that point, I'm actually going to do number, I think it was number 18, wasn't it? Yeah, let's do number 18. So, same basic properties. Again, go through the same basic steps each time. Number 18. Number 18 has f of x is equal to negative 5 x cubed plus 16x squared minus 9. And the factor we're looking for is x minus 3. Okay. Step 1, synthetic division. For synthetic division, I write out my piece. We have negative 5x cubes. I have 16x squareds. I don't have any x's, and I have negative 9. Okay, my number here is going to be a 3, because remember I have negative 3 there. Remember, to find that result, I take x minus 3 equals 0. Solve both sides. I end up with 3 as the solution, which is where that 3 comes from. All right, let's do it. So drop the negative 5. This becomes negative 5. Negative 5 times 3 is negative 15. 16 and negative 15 makes 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. 9 and negative 9 is 0. Ooh, look there. Wow, that was good. Okay. Which means that I have done step 2 now. It does in fact equal 0. So step 3. I rewrite using my x minus 3 and the quotient, which is negative 5x squared plus x plus 3. And now, just like before, I'm going to use the AC method. So we need to factor this. And I'm going to again use the AC method. AC is not the only method. Remember, there's other methods you can use to factor these kinds of functions. It's just the one I prefer. So there I'm using it. Okay. So I have x minus 3 times, all right, my AC. Okay, I take negative 5 times 3, which is negative 15. I should together get 1. Those would be that crazy? I don't like these vectors. Yeah, this does not factor. And so if it doesn't factor, I would assume we need to leave it right here. Now, if it doesn't factor, there is one more thing you can check. So I tried the AC method, and the AC method didn't work. And if I try standard factoring, it doesn't work either. So what I'm going to do is my last resort, I'm going to try the quadratic equation. Remember, the quadratic equation allows me to find factors indirectly by using negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's see what we get. Negative b, that'd be negative 1 plus or minus the square root of 1 squared minus 4 times negative 5 times 3 all over 2 times negative 5. So negative 1 plus or minus square root of 1 squared is 1. Negative 4 times negative 5, that'd be positive 20. Times 3, that'd be positive 60. All over 2 times negative 5 would be negative 10. Which means I end up with this, negative 1 plus or minus the square root of 61. All over negative 10. And this is not going to be a nice number, so I'm probably just going to leave it this way. So it's possible when you do these kinds of problems that it doesn't actually work out. Do check my work on this one, just in case I did make a mistake. But there is a possibility that this is not actually going to factor any farther. Now, it does say to find all real zeros, which we actually have found. So, the real zeros, this function would be 3, which comes from what we started with, and this one. These would be our real zeros. So the question said, hey, use the factor theorem to find all real zeros. We did. On the previous problem, number 14, to reiterate that fact, the real zeros, always make sure you read your directions, otherwise you might miss something like this. The real zeros, well, there'd be 1, obviously, which comes from this term. And there'd also be 2, which comes from the third term. This last one would be 3 halves. So, for our notes, if it asks to find the factors, so this would be my notes, to find real zeros. What does that mean? Well, what it means is, take each factor equal to 0 and solve. So for example, if on this one, like I would include this piece as my example. If I have factors, if I have factors of x minus 1, 2x minus 3, and x minus 2, my zeros would be 1, 3 halves, and 2, which is just when x minus 1 equals 0, when 2x minus 3 equals 0, and when x minus 2 equals 0. And so if the question asks you to find the real zeros, if you can find the factors, you can find the real zeros. And the question becomes, can you find the factors? Which we have a factor theorem to now help with this. Isn't that crazy how it all fits together? Look at that. So beautiful. So nice. Okay. Now, Here's the thing. The factor theorem works best when I'm given a factor, because then I can use, we've seen two techniques now. We can use the AC method, along with synthetic division, to find the factors. Or we could use, this little nastier method, where we used the quadratic equation to find it. But I want to, just for a second, look at what's happening next. The next few problems on our homework. It says, use the rational zero theorem to find all zeros, but notice they haven't given me a factor. Well, that's because the rational zero theorem, along with a couple of other theorems, allows you to take the information given in a single problem and solve it. So, let's take a look now at number 22 before I add to the notes, because I want to discuss as we go through kind of how you would do this using the theorems we're going to discuss as we go. So 22. So 22 is x cubed minus 3x squared minus 10x plus 24 equals 0. So the question becomes, if I don't have a 0, where do I start? Well, that's why for these problems, we're going to note a couple things. First off, the remainder theorem. Oh, sorry, it's not called the remainder theorem here. It's called the rational zero theorem. We already did the remainder theorem. Okay, the rational zero theorem. Let's go up to it. I'm excited. This is, in my opinion, one of the best parts of this book. Like, in terms of actually interesting and fun math. I know you may not think of math as being fun, but this to me is the fun part. Okay, let's read the rational zero theorem. Boom. Okay, it's got a lot of words to this. I do want to point out that there's a piece that's actually better to think about. Right there. Okay. The rational zero theorem states that if the polynomial f of x equal to a to the n x to the n plus blah 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 has integer coefficients, then every rational zero has the form p over q, where p is a factor of the constant term a of 0 and q is a factor of the leading coefficient n of n. Boo. That sucks. I hate reading that. So here's how I'm going to write this. The rational zero theorem states that the rational zeros of f of x are factors of p over q. In this case, p is the leading coefficient, and q is the constant. Wait. I have these backwards. I always do this the first time. Where q is the leading coefficient and p is the constant. Where q is the leading coefficient and p is the constant. So let's talk about how we approach number 22 with this theorem in mind. What does this mean? That means that we can actually find a list of all possible zeros. And in fact, for some of your problems, this is all you have to do, because this is going to be so complex by itself. But here's the thing. The list of all possible zeros just means a list of all possible p over q. So for this problem, let's go through some pieces. My p in this case, is 24. My q in this case is 1. So what's this mean? Well, it means my full list of all the possible zeros is as follows. 24 over 1. That's the first possibility. But also negative 24 over 1. So this is just p divided by q and negative p divided by q. This is because for p, the factors of P are 24 and 1, negative 24 and negative 1, 12 and 2, negative 12 and negative 2, 8 and 3, negative 8, negative 3, 6 and 4, negative 6, negative 4. So these are all the possible factors, which means that this list is just each of these top numbers divided by each of these bottom numbers. On the other hand, Q, its possible factors, would be 1 and 1, and negative 1 and negative 1. I'm not including decimals because, quite frankly, the decimals aren't worth it. They're not technically rational, and this is called the rational zero theorem. So let's take a look, shall we? We go through the list and explain where the list comes from. 24 over 1, negative 24 over 1. 12 over 1, negative 12 over 1. 8 over 1, negative 8 over 1. 6 over 1, negative 6 over 1. 4 over 1, negative 4 over 1. 3 over 1, negative 3 over 1. 2 over 1, negative 2 over 1. And 1 over 1, and negative 1 over 1. This is every possible thing that could be a 0. So 24 over 1 could be a 0. Negative 24 over 1 could be a 0. 12 over 1 could be a 0. Negative 12 over 1 could be a 0. 8, negative 8, 6, negative 6, 4, negative 4, 3, negative 3, 2, negative 2, 1, negative 1. These could all possibly be different zeros. And so for a much cleaner list, I'm going to use some shorthand here and simplify some. 24 over 1 is just 24. Negative 24 over 1 is just negative 24, so I'm going to do plus or minus 24. 12 and negative 12 would just be plus or minus 12. 8 and negative 8, plus or minus 8. 6 and negative 6, plus or minus 6. 4 and negative 4, plus or minus 4. 3 and negative 3, plus or minus 3. 2 and negative 2, plus or minus 2. 1 and negative 1, plus or minus 1. Which means, in theory, if I really wanted to, I could just test all of these using the remainder theorem. I could use synthetic division and test to see if any of them end up with a remainder of 0, and then combine that with the factor theorem. I should be able to find out if it's actually a 0 or not a 0. Which means I could take number 22, I could use synthetic division with 24 and see if it works. And if it does work, it's a factor. If it doesn't work, then I could try it with negative 24. Then I could try it with 12 and negative 12. 8, negative 8. 6, negative 6. 4, negative 4. 3, negative 3. 2, negative 2. 1, negative 1. I could just sit there, and this is what I refer to as the grunt method. I could just test every single one of these. And in fact, at the start, that's kind of your best option. But this is a long list. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different things you would have to test. And oh dear Lord, do I not want to test them all. So there's some things that actually help you do this a little faster and a little easier. Now, notice the how-to. It states, determine all the factors of the constant term and all the factors of the leading coefficient. That's the first thing we did. It's right up here. So this right here is step 1. Step 2, determine all possible p's over q's. Well, that's this list, which is much better and concisely put here. And then it says, determine which possible zeros are actually zeros by evaluating each case. So what the book is advocating is go in here and try all 16. Oh my God, no. Not going to happen. It turns out the nice thing about the rational root theorem, or rational zero theorem, as it's sometimes called, is that no matter what you do, If you find a 0, you can do the process over again. And so, this is what a worst case scenario of this function looks like. I'm going to attempt to find if any of these 16 works. So, I'm going to start by doing synthetic division of the function. 1, -3, -10, 24. And I have to essentially do this at -24, and then I have to do it again at +24. I have to then do it again at -12, and then again at +12, and then again at -8, and then again at +8. And then I have to do it at -6, and then at +6, -3, +3, -2, +2, -1, +1. The book is advocating doing every single one of these. Okay, so I'm going to do it once. Just once am I going to do 22 the way the book says to do it the first time. And you can see down here below how they walk their way through it and try it out. Now, do note that they, just like us, have listed out all possible zeros into this list. Okay? And then, just like us, they're going to be evaluating and seeing which of these work and which of these don't. Notice that those, they only tried 3 of them and none of them ended up working. So, let's try some things out. Ooh. Okay. Just as a quick sub point here. If it says find all possible zeros, like this list right here, is just like number 56 and 58, which I'll do later on. Okay, let's do it. My goal is to see if it's going to work. You will quickly find that some of these do not work because you can just tell right off the bat that's not going to. So we'll get 1, -3, -10, 24, 1, -3, -10, +24, 1, -3, -10, +24, 1, -3, -10, +24, 1, -3, -10, +24, 1, -3, -10, +24, 1, am I going crazy yet? It sounds like it. -10, +24. Okay. I really don't want to do this. Okay. 1, -24, -27. And right there, I'm going to go ahead and stop. Because -24 times -27 is going to be a really big number. Like this ends up being positive 638, I think. And I know that's never going to work. Because -10 of that is 628. And -24 times that is going to be a really big negative number. I know 24 is not going to work. Using some logic and reasoning can really help out. Because it can tell you, hey, dummy, we should probably stop because it's not working. And same thing happens on 24, too. 1, 24, 21. 21 times 24 is 503. Minus 10 would be 493. And so again, I can see that's never going to work out. I do not have to finish the problem to get this answer. Okay? I just want to know if I'm going to end up with 0. And I'm never going to get 0 by taking 493 times 24 and adding 24 to it. It's never going to work. Use some intelligence, people. Be smarts. Use smarts. Use them. 1, -12, -15. 12 times 15, that should be 180. 180 -10 is 170. 170 and that's not going to work. There's no way I'm going to possibly get to 0. Okay? Use some intelligence here. Positive 12. So 1, 12, 9. 9 times 12 is 108. That becomes 98. 98 times 12. No way. There's no way this will get to 0. So 12 is out. See how I'm just eliminating pieces one at a time? And notice I'm never really completing any problems because my goal is it going to be equal to 0? I already know what the answer should be. If I'm not getting 0, then I should stop. Okay? Next. 1, negative 8, negative 11. And this will become 8 times negative 11. Positive 88, which will become 78. 78 times negative 8 is going to be a big negative number. It's never going to work. I'm never going to get 0. Okay, positive 8. 1, 8, 5, 40, 30, 2, 4. Nope, didn't work. Never am I going to get 0. Okay, negative 6. 1, negative 6, negative 9, positive 54. That would become 44. And negative 6 times 44 is too big. So I know it's never going to get to 0. I know negative 6 is out. Okay, 1, 6, 3, 18, 8. That's close. That's real close. Let me double check, make sure I didn't make any mistakes. Oh man, that is so close. 6 times 8, that's 48. Which again, it's not 0, but it's close. I mean, look at that. That is so much closer, so much smaller numbers than what I've been getting in hundreds and thousands. Okay. Next, let's try the negative 3. 1, negative 3, negative 6, positive 18, 8, negative 24. Oh my gosh. I got 0. So what's that tell me? That tells me that negative 3 is a factor. Which tells me even more. That tells me that one of the answers is x plus 3. So if I know negative 3 worked, that tells me it's a factor. And if it's a factor, it is x plus 3. Now, I'm going to keep going. 1, negative 3, negative 10, positive 24. Go ahead and finish the rest from 1, negative 3, negative 10, positive 24. 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 Okay. Woo-wee. Now, I'm going to come back to this one here later because I'm going to showcase some other things you can do to shorthand this process because, oh my lord, is this bad. Like, who wants to do this? I love math, and I ain't wanting to do this any point in the day. So, like, what else can I do to make this a little easier? I'll show you in a second. So, let's go ahead and continue. Now with 3. So, 3 times 3 would be 9. Sorry, 1 times 3 would be 3. Negative 3 would be 0. 0, negative 10. This becomes negative 30. Because negative 6, that didn't work. Because I'm supposed to get 0. I didn't get 0. So, 3 does not work. Okay. I tried negative 2. 1. Negative 2, negative 5, positive 10, 0, 0, 24. I did not get 0 at the end, so I do not get negative 2 as an answer. Trying 2 now. 1, 2, negative 1, negative 2, so you get negative 12, negative 24, 0. Boom. Next answer has been found. So I now know this is an answer, which means I now know 2 is an answer, which means if 2 is an answer, that means x minus 2 is an answer. Okay, now I can keep going. I can check the last 2. I believe at some point in time a mistake was made, but that's okay, because this method is just kind of an example to showcase kind of the worst case scenario. 1, negative 1. Oh, I know what happens. Negative 4 and 4 becomes negative 6. That becomes 6, which becomes 30. So since I did not get 0, I do not get this an answer. And then I try 1, same thing. 1, 1, -2, -2, -12, -12, 12. Did not get zeros and answers. This is not an answer. So I get two factors. I got x equals -3 and x equals 2, which means I have x plus 3 and x minus 2 as my two answers. Now, let's continue with our notes. Okay. Continuing with our notes. The fundamental theorem of algebra. The fundamental theorem of algebra appears in many forms. We talked about a few of them already, but this one's kind of the main form, the one that everybody in math kind of recognizes as the fundamental theorem, because the other theorems are more fundamental theorems of arithmetic. So let's talk about the fundamental theorem of algebra. Now, most of this is not very useful. It's actually kind of confusing. So it states that the fundamental theorem of algebra states that if f of x is a polynomial of degree n, which has to be bigger than 0. That's a big detail there. It has to be of degree, because it's a polynomial, and that degree has to be bigger than 0, because degrees of 0 actually don't do anything. Then, f of x has at least one complex 0. We'll get back to what that means in a little bit, but for now we're going to go ahead and move on. Given this argument, the big detail to point out is that f of x, is the last line, will have n roots if we have multiplicity. Okay, so what does that mean? I'd like to go back to number 22. What does this tell me? Well, it tells me on 22, if I look at this function, I can see that I have x cubed minus 3x squared minus 10x plus 24 equals 0. What this tells me is, because of this 3, this tells me I should get 3 factors. That's what that 3 tells me. Notice that for number 22, I did not get 3 answers. I only got 2. I got -3 and 2. But that's why that last line is so important. If we allow for multiplicity, we talked before that multiplicity means you have duplicate answers. What that means is these 2 are the answer, it's just there's one more. And it's either another -3 or another 2. So the question becomes, is there a better way to do number 22? Like, is there a faster way to take 22, to solve it, to get a solution? Well, it turns out, for our next piece of notes, kind of like the way to go for finding all factors. What's the process? Step 1, it helps to list all possible factors. That is what we did right here. That's this process right here, where we look at P, we look at Q, we define what P and Q are, we find all the possible factors of P, we find all the possible factors of Q, and we divide every single one of them to get a full, big, long list. We're going to do a couple of these. So get used to finding this list, and you get used to finding it quickly. Once you've got that list, you need to find one root. You need to do whatever it takes to find one, which means that the first step was not avoidable. Doing these to get to -3 was not avoidable. Now, we can choose to do it in any order we want, so being intelligent in our guessing can be really helpful. However, there's no real way to get around this first part of the process, to getting to -3. It's just impossible. You cannot get past this process of checking these. Okay? And here's the thing. If you got a big list, that can be real intimidating. So I'd recommend some recommendations for you. When you try to find one root, I have some recommendations. Number one, try easy roots first. I cannot stress this enough. Like, starting with 24 is the worst possible decision you can make. Like, negative 24 and 24, these are big numbers. And when I plug them in, I'm going to get big answers. The odds of these working are relatively small compared to everything else. Like, unless you have big numbers in the problem, you're unlikely to have big numbers in the solution. So start easy. Start with the ones or the twos, the threes, the fours. Like, start here. These are far more likely to be answers than anything up above. It's just true. Okay? And then if you fail at that, make sure to try negatives. Like, don't forget about the negatives. Don't sleep on them. Because remember, for every number you find, the negative is also included. So we found 24 by doing a factor of 24 is 24, obviously. A factor of 1 is 1. 24 divided by 1 is 24. But 24 and negative 24 also work. Next one. Once you've found one root, you can either keep going, keep trying more roots, or option A, if you're down to a quadratic, you try factoring. If you're not very good at factoring, you may decide just to keep going. Like, if you suck at factoring, you may just decide to be like, hey, I'm going to keep doing these over and over and over again. If you don't like factoring, you may end up trying, instead of factoring, you may try like the quadratic formula. Until eventually, you may also try the rational factor or rational zero theorem again. So, let's go back and look at 22. Now that I've got my new notes. Okay. And if you didn't notice, I actually skipped 2 numbers, which is why I didn't get all 3 answers. I did not test negative 4 and positive 4, and one of those is the other answer. So, okay, let's try 22 again. Like I said, there's no way to get around testing the first couple. You just can't, okay? But now let's assume we got to try negative 3. So this is number 22, abridged. Let's assume we tried all those other ones, and then we try negative 3, and we get this result. So we had 1, negative 3, negative 10, positive 24. So we got 1, negative 3, negative 6, positive 18. We got 8, negative 24, and 0. Well, once we get to here, we could, decide I want to take a pause. And instead of continuing down the list, I could, as my branching options, I could think of this as x squared minus 6x plus 8, and now I can factor. Because remember, that's what this statement is. We could totally do that. Alternatively, I could take the exact same equation. I could try the quadratic formula. Remember, my goal is to get down to here, okay, by any means necessary. This theorem is a way to get started. But once you get past those first couple steps, you want to start going back to easier stuff. This is only really useful to get that first couple steps in. Okay? So we could try this. Once it's in this form, once we get down to quadratic, we could factor it. We could use a quadratic equation. We could also just continue from here. The rational zero theorem applies to any equation, including this equation. So I can now make a new list of possible p's over q's and use those to get farther from here. Because I wouldn't want to try 24 if I haven't already. Because 8 is never going to get me to 24. this equation cannot possibly have 24 as a factor. For example, this would have factors of plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1. Like, look how much smaller this list is compared to the first list. So once I find one of these pieces, I can eliminate a whole bunch of these, which is equally important to try the easy ones first. I want to try the easiest thing I can possibly do first. Now, with this list, I can now sit there and be like, okay, let me now try anything I haven't done yet. Now notice, in this one, I had already tried 8 and negative 8, so I shouldn't try it again, because if it didn't work before, it's not going to work now. Like, trying negative 8 and positive 8 is just stupid. It's never going to work. So I might immediately be like, okay, well, let's try 4 and negative 4, and see if they work. Or I might try 2 and negative 2, or 1 and negative 1. But I need to use some logic and reasoning to get through this. So 22 I'm going to put on the back burner. I'm now going to attempt to do the next one, which is 28, from start to finish, using every trick that I can. So let's list out a bunch of stuff when we start. 28. We have 2x cubed plus x squared minus 7x minus 6 equals 0. Okay. So let's look at how I can do this. First, I know I should have 3 solutions. How do I know that? Because that 3 right there. I should get 3 solutions somehow. Next, because I know I should get 3 solutions, I should look at what those solutions look like. So I do P over Q. And I start making my list. So my P in this case is 6. My Q in this case is 2. The factors of 6 are 6, 3, 2, and 1. The factors of 2 are 2 and 1. Let's start making our list. Now when I do this, I like to think of this like FOIL. So my factors would be 6 over 2, 3 over 2, 2 over 2, and 1 over 2. And I also have factors of 6 over 1, 3 over 1, 2 over 1, and 1 over 1. Let's go through the full list. 6 over 2. And I should check both answers. I have 3 over 2. Plus or minus 2 over 2. Plus or minus 1 over 2. 6 over 1. Plus or minus 3 over 1. Plus or minus 2 over 1. Plus or minus 1 over 1. Now, before we go any farther, you may notice that some of these are duplicates, right? 6 over 2 is the same as 3 over 1. And 3 over 1 is just plus or minus 3. 3 over 2 is unique. 2 over 2 is just the same as 1 over 1. So I'm not going to double up. That's just silly. Plus or minus 1. 1/2 is unique. Six over 1 is just 6. 3 over 1 is just 3, but I've already got 3. 2 over 1 is just 2. And 1 over 1 is just 1. So this is my list. So these are the possible solutions. Now keep in mind, I only need 3 of them. So maybe I have 3, 6, and 2. Maybe I have 3 halves, -1, and -1/2. I don't know. I don't know. But it's got to be one of these. Or in fact, it's got to be 3 of these. So let's now jump straight to step 3, which is synthetic division. My function is 2, 1, -7, -6. I need to choose where to start. Now, first thing to know, Starting with 3/2 and 1/2, probably not the best choice. Like, eventually I could try them, but probably not the best ones to start with. That is because they're complicated. They're fractions. Like, the odds of them being nice are really, really low. And so it's far better to start with easy ones. Remember, easy is good. And big ones are probably also a bad place to start. So 3/2 is probably out. 1/2 and 6 are probably all bad answers. Like, they're answers, they're allowed, but they're not good ones. Like, I wouldn't want to start with those. Now, if I try 3 and -3, 1, -1, 2, and -2, and none of them work, then I'll go back and try those. Don't get me wrong. I will go back and try those eventually. But this is not a good place to start. Now, at this point in time, I'm going to show you my shorthand for this. I'm going to try 3. Let's see what happens. If I'm lucky, maybe it'll work out right away. So when I try 3, I would get 2 because it drops. 2 times 3 is 6. This becomes 7. 7 times 3 is 21, which becomes 14. 14 times 3, I know 3 isn't going to work. So immediately, I jump down, and now I'm going to try, instead of 3, let's try -3. So, 2, -3. So again, I'm going to the top number here. -3 and 1 would be -2. -3 and -2 would be -6. -7 and -6 is -13. That's also not working. So the +3 and the -3 are out. Okay, so again, I'm at 2, 1, -7, 6. Some people like to do them separately. Like, that works. You're welcome to do that. In fact, I might show that next. So I would come back here and be like, okay, let's try it again. But now with, I'll do this one, 2. So we do 2, 1, -7, -6. And some people will just do a lot of mental math and save themselves some headaches. This becomes 2. 2 times 2 is 4. Plus 1 is 5. Times 2 is 10. -7. This becomes 3. This becomes 6. Oh my gosh. 0. So what's this tell me? This tells me that 2 is a factor. Well, technically it tells me 2 is a 0, which tells me that x minus 2 is a factor. Now, here's what I mean when I say you can do things intelligently. This is now a quadratic. We now have 2x squared plus 5x plus 3. From this point, now that I've found one solution, I can use a quadratic equation. I can attempt to factor. Like, there's all kinds of things I can do here. And in fact, for this one, I'm going to factor just to get the process done a little faster. So, notice I use the rational zero theorem along with the remainder theorem and the factor theorem to get one of the answers. But once I've got one of the answers, like, I don't bother using it more because it's hard. I'd use instead the other theorem. Adding them together gives me 5, multiplying together gives me 6. That'd be 2 and 3. So now I can do 2x squared plus 2x plus 3x plus 3, and I get this result. 2x times x plus 1, 3 times x plus 1, and I end up with these answers. My answers would be 2x plus 3 and x plus 1, which means my factors would be 2x plus 3 and x plus 1, which means my zeros would be, let's see, so this gives me the +2. This one would give me -3/2. Just solve for each piece. And this one would give me -1. And so if I did keep going, this would still work. If I tried -2, it wouldn't work. If I tried 1, it wouldn't work. If I tried -1, it would work. But once I get there, like, I've run out of the easy ones, and now I got to try the harder ones. But notice how I use the information I have to make this process a little faster, right? I found an easy one first, and then dropped the hard thing to try with an easier alternative, right? I can use the AC method. I've got a lot of experience with that, and so I can do that quickly. However, if I wanted to, I could just keep going from here. Now that I'm down to this equation, don't ever go back to the original if you don't have to. Once you've found one factor, use the new equation. So now I can test 1 on this equation. 2 times 1, or 1, 2 times 1 is 2, 5 and 2 is 7, 7 and 1 is 7. This gives me 10, didn't work. So now I can again try 2, 5, and 3 with now negative 1. 2 drops, 2 and negative 1, that would be negative 2, which gives me 3. 3 and negative 1 gives me negative 3. And of course it ends up being 0 because we know it's going to work. Like, don't ever go back to the original if you don't have to. I'll do one more of these, showcasing again a bunch of different shortcuts and tricks you can use. You can see, as you might imagine, these can take an incredible amount of work. Just a lot of components to them. And that's why I'm going to extend this assignment a little bit, because these do take time. Let's look at one like, what's the nastiest one I can find? Let's talk about 38. 38 looks simple, but it's really not. 38, we have 4x cubed minus 3x plus 1 equals 0. Okay, let's do this. 4x cubed minus 3x plus 1. So first of all, let's list the possible p's over q's. So my p is 1, my q is 4. The factors of 1 would be 1 and negative 1. The factors of 4 would be 4, negative 4, 2, negative 2, 1, and negative 1. Which means my factors, my complete list, which again, number which one is it? This one. 57 and 59 just ask you to list the possible zeros. They don't ask you to actually solve. So if we're doing 57, it would just stop right after this step. Go back up. So my possible zeros would be from the list. So 1 over 4, positive and negative. 1 over 2, positive or negative. And then 1 over 1, which is 1, positive or negative. So this has 6 possible zeros. If I want to try this out, I'd have to either try all 6 or get to where I can find 1 and then shorthand the rest. So I'm going to take this list. If this was number 57 or 59, I would stop right here. But it's not, so I'm going to keep going. I have 4x cubes. I have 0x squareds. I have negative 3x's, and I have 1 constant. Now, I need to try these out. Now, again, I could start with the 1/4 and the negative 1/4. I'm not going to. I'm going to start with the easiest thing I got here, which is 1 and negative 1. Because if I'm lucky, one of those will work. If I'm unlucky, I can still go back and always try these harder ones later. Start easy. So I'm going to try 1 and see if it works. 4 would drop. 4 times 1 is 4. 4 plus 0 is 4. 4 times 1 is 4. 4 times 0 is 0. Negative 3 and 4 would be 1. 1 times 1 is 1. This gives me 2. 1 did not work. So go back and try again. 4, 0, negative 3, 1. Now I'm going to try negative 1. 4, negative 4, negative 4, 4, 1, negative 1, 0, boom. Negative 1 worked. Okay? Notice how I chose the easy ones first because those are just faster and easier to use. From here, I have 4x squared minus 4x plus 1. Now here's the thing. I could continue trying these factors. I could make a new list of factors with these p's and q's, or I could jump to something else. This time, instead, I'm going to go to the quadratic equation. It's an option, just like factoring is an option. So that's what I'm going to do. The quadratic equation would state negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a All right. 4 plus or minus negative 4 squared is 16. 4 times 4 is 16 times 1 is 16. 2 times 4 is 8. 16 minus 16 is 0, so we end up with 4 plus or minus 0 over 8. 4 plus 0 is 4 over 8, which is 1/2. 4 minus 0 is 4 over 8, which is 1/2. Which means I end up with 2 different 1/2s, which means I have, as my zeros, I have -1, and then 1/2 multiplicity 2. If I want to find the factors, this would be x plus 1 and 2x minus 1 squared. You can always convert backwards by just doing the opposite steps we would to find it normally. Taking x equals 1/2 and then solving for the 0. Notice it has to be squared because there's 2 of them. One for when we added, one for when we subtracted. 2 different answers because the quadratic equation should always give 2 answers. It's just they may be multiplicity. So it's multiplicity 2. If, however, I did not use the quadratic equation and I had tried -1 and it worked, and I was left with 4, -4, and 1. I could go back and try -1 again to check to see if it has multiplicity, because I know -1 worked once. Why not check it again? Or I could go back and try, 1/4 and see if it works. It doesn't. I could try -1/4. It doesn't. I could try 1/2, and it does. And the result I will get will be 2x minus 1. So we'll take a watch. If I did the 1/4, never mind, screw that. No, it's too late. Okay. The last thing I will tell you is these problems here in the middle involving Descartes' rule of signs. I'm going to ask you to read through that little piece. There's a great example of this in 410. So please look at page 410. We've run out of time. So I'm giving you some extra time. I may cover this a little bit on Saturday because I want to make this a 2-hour video. Let's do that. I'll just do the Descartes rule of sign tomorrow along with any questions from the section so far. So we'll do Descartes rule of sign. And that'll be on tomorrow's video. I can't spell tomorrow. You know what? The school's out. Not really, but still. So we'll stop right there. Your homework for tonight, and it'll be due, remember, on Thursday. That homework assignment will be somewhere. Jeez. So many pages of notes. There it is. Took like 9 pages of notes today. Wow. What a good day it was. Section 5.5, page 412/430, 1 through 59, every other odds. That'll be it. We'll go through Descartes' rule of signs in a short video tomorrow, along with any questions I've received so far. And that'll be it. I hope you guys have a good weekend. Remember, this will be due on Tuesday instead of the normal Saturday. And that'll give you some extra time. Have a good weekend, and I'll see you guys tomorrow.